lecture. So remember, we have been talking of topological groups last time. Last time we introduced topological groups. We said there are groups which are not topological spaces. We call them abstract groups. On the other hand, there are topological spaces without any group operation or anything. We combine these two concepts together, we get a topological group, which is a set with a product and also topology. Product meaning group product. And these are compatible in the sense that the group operations are continuous. There are two group operations. One is the binary multiplication and the other is inverse. Both these maps are continuous. So we started giving examples of topological groups, and it turns out that most of the nice groups you have met are indeed topological groups. Of course, there are finite groups. Those are discrete groups. So again, topological groups. But the infinite groups, you know, various things like R, etc. The addition is continuous, multiplication is continuous on R star. Matrix multiplication, matrix inverse, we all showed to be continuous with respect to the natural topology on invertible matrices. So we were able to give many nice examples of topological groups. Here was the exercise that showed that GLNR is a topological group. It's an open subset where determinant is non-zero. So things like determinant is a continuous map, blah, 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 1 upon a non-zero thing, continuous is again continuous, etc. All these properties we had proved earlier, and they heavily use the categorical formulation of universal properties of product. All the time we use that. And the categorical formulation of an embedding. Then we came to very interesting topological groups, line and circle, and there's a very nice relationship between line and circle, namely the exponential map or sine and cos in Cartesian coordinates, exponential map in complex coordinates, sends you from line to circle, and that map sends any point t to e to the power 2 pi I t. So here was the map. T goes to e to the power 2 pi I t. Here's the map. And then we did various exercises like what are all continuous homomorphisms from R to R? Those were scalar multiplication. What are all the continuous maps from R into S1? Well, there are plenty of those. They are of the form cos of Ct, comma sine of Ct, where for C you can take any real number. What are the continuous maps from S1 to S1? Those are of the form z to the power constant, where the constant now has to be an integer. Just now Sonakshi just was asking why it is so, and I sketched a proof. Maybe some of you are not yet present and the recording had still not started. Okay, so I have not spoiled the exercise for those of you who missed it. And I also asked just now, what are all continuous homomorphisms from circle into line? And the answer is there's only the constant one sending all of the circle to the point 0. There's nothing else. Prove it. That is exercise. Okay. So let's continue with topological groups and continuous homomorphisms. And today I want to discuss the Hausdorff property for topological groups. And then I want to talk of discrete subgroups and talk of examples. But let's begin with talking of homogeneous metric spaces. Are you familiar with the word homogeneous? Yeah? Can you hear me? This is the test. Hello?
Yes, sir.
Sonakshi, are you the only one present even now? Okay. So homogeneous means the same all over. Okay. So blender in the kitchen homogenizes whatever smoothie you are making. So it becomes. Otherwise, there is a lump of banana and another lump of apple and whatnot, and you turn your mixer on, and then it becomes homogenized. It becomes the same all over. So homogeneous. Okay. Homo means the same. Homomorphism means keeps the same form. Okay. All right. So let us define a homogeneous metric space as something as follows. So let me switch to my pen. Let me take the color X D. is homogeneous if for any x, y belonging to x, there exists a distance preserving isomorphism, meaning the map is distance preserving, it is therefore necessarily injective, it's also surjective, and so its inverse is also distance preserving. That's why it's isomorphic. That makes an inverse. F from x to x such that f of x equal to y. So look at this definition, stare at it. Any 2 points are like the same because there is a self isomorphism of that metric space which preserves all distances, and it's a bijective map, so that the first point becomes the second point. So really, nothing changes. Okay. So this distance preserving isomorphism, self isomorphism, automorphism. There is one which takes one point to another, any given point to any other given point. Then you say the metric space is homogeneous. Now, give me an example of a homogeneous metric space. Chalo. Hello, hello. No chorus of voices.
Are real number with usual
Sonakshi,
metrics.
are you the only one here? I want to hear just one other voice to reassure myself that I am not lecturing to one. Chalo, somebody open your mouth. Awaaj karo. Sonakshi, I am going to close this lecture and I am going to make a private video call with you. And we will continue the lecture there.
Now, what is going on? I have a class.
No, I don't know whether there is any audience at all.
Sir,
Yes, sir.
Only one person is responding. I again and again asked whether there is any person in the audience other than Sonakshi. Is there any answer?
Yes, sir.
Who else is there?
Who were in my room?
Sorry, name.
Hello, sir.
Okay, so now I hear some other voices. All right, you see, otherwise I decided to simply conduct a one-on-one lecture because then I can ask the student and have a much better conversation. But otherwise, I don't see why I should lecture in this. If there's only an audience of one, it might as well be a private tutorial. Okay, so now answer my question. Give me examples, or give me an example of a homogeneous metric space.
As Sonakshi said, R with usual numbers, with usual metric.
Okay, R with usual metric. R usual metric. X minus 5. Why is this homogeneous? Tell me.
I can define the map f of x is equal to x, the identity map itself. And that map is distance preserving also and also an isomorph.
No, I want, given any 2 points, I want to take one point to the other in a distance preserving way. So what should I do?
The map f of x is equal to x will work.
F of x equal to, yeah?
X.
No, that will only take the point to itself, won't take it to y. I want f of x to be y.
So you translate forward?
Absolutely. F of x equal to x plus c. This preserves all distances, right? Yeah?
Yes.
And if I want x to go to y, choose c to be y minus x.
Y minus x.
So define in general f of t equal to t plus c, where c is y minus x. You see, you are just translating the line. You are taking this line and shifting everything. Shift by c. This is a distance preserving self map, right? It's bijection, right? And by adjusting how much you shift, you can consider, you can make the first point into the second point. Sabko samajh gaya kya? Was it really difficult? That's why all points are very similar as far as the metric space R is concerned. Now let's consider a non-example. Let's take 0, 1. Okay, usual metric. Now one point I take 0. The other point y I take 1/2. Is there, what are the distance preserving maps of 0, 1 with itself? Tell me. Distance preserving isomorphisms. Tell me. X equal to. Tell me what are all x, x. Distance preserving self isomorphisms. So you see, now we are not talking category theory. We are talking concrete geometry. We are talking mathematics. And now you guys should be able to very happily answer. I heard that many of you like mathematics and don't like category theory, whatever that is. So here's mathematics. So chalo, bolo. Very simple mathematics. You should be very happy and rapidly answering. So what are the distance preserving self isomorphisms of 0, 1? Not even one reply? Give me some at least. How about identity map? Does it preserve distance? Yes or no?
Yes, sir.
Yes, sir.
Why are you guys so silent and unresponsive? May I understand? Okay. Otherwise, you can read books. You see, what's the whole point of conducting schools? The point is so that there can be interactive learning. Okay. So identity is definitely distance preserving. Can you give me anything else which is distance preserving self isomorphism? One more de do.
So line joining any 2 points.
No, no, no. My x is this interval. Now give me a distance preserving self map. This is simple geometry. Kya? Just flip the interval around. No? Send 0 to 1 and 1 to 0, and every point send any t to, where will you send? 1 minus t. This is distance preserving, right? Because what is mod x minus y? Well, is it equal to mod 1 minus x minus 1 minus y? Yes, because this is equal to mod of y minus x. So distance is preserved, right? Very simple, na? Why didn't you think of it? Here's an interval. I want a self map which preserves distances. Just flip it around the midpoint. It preserves distances. समझ गया क्या? Have you understood the idea of distance preserving self isomorphism? See, this is the problem. You guys know what is an automorphism of a field. You know it's an automorphism, inner automorphism of a group. That's group structure preserving self map. In metric spaces, what will you have it with this? The distance preserving maps. You will want a self bijection which preserves distances. That's the structure you are given here. Yeah. Okay. So let me ask you for a general answer. Okay. Here. Exercise. Find all automorphisms of RD, usual metric. Metric preserving self bijections. So find out. And the answer is going to be something very nice, which you have known all along. And in fact, it has a nice topology, making it a topical group. It's very important in the avatar as a topological group. This is a group. You see, all automorphisms always form a group because given an automorphism of anything, it may be automorphisms of in any category. It may be automorphism of a group, it may be automorphism of a ring, it may be automorphism of metric space, it may be a self-homeomorphism. Composite of two such is again another such, or the inverse is again another such. And composition is obviously associative. So automorphisms always form a group. So they're always automorphism groups. Galois was the first one who realized the importance of automorphism groups in field theory, number theory, etc., etc. But Euclid was already using automorphisms. Let me remind you how Euclid used automorphisms. Euclid said that one triangle is congruent to another triangle, or one figure in the plane is congruent to another figure if what he called a rigid motion, if you can move the plane so that the first figure coincides with the second figure. And that move it rigidly means don't change any distances between points. Okay. What does it mean that some stick is rigid? Rigid means when you move the stick here and there, the distances between points do not change, right? So all isomorphism in Euclid is defined in terms of distance preserving self-isomorphisms of the plane. Two figures are congruent if a distance preserving self-isomorphism of the metric space, which is the Euclidean plane with its usual Euclidean distance, carries the first figure into the second figure bijectively, then those two figures are called congruent. So you have always known this. Am I right? You have always known this? Hello, hello? So when we started talking of distance preserving self maps, did you remember your school geometry and congruence? You should have. Now in hindsight, you'll realize you should have. And that's because you have forgotten your school geometry, perhaps. You know, all mathematics is an integrated subject. One part built on the other, built on the other, built on the other. The metric spaces that we are doing now and the topology we are doing is a continuation of Euclid. So we are talking of distance preserving self-isomorphisms. That's at the foundation of Euclid. It is the foundation of congruence. Okay, enough of this. I asked you to determine, but you see, Euclid didn't have the notion of group. He had these self-isomorphisms, but he didn't say that all those self-isomorphisms form a group. What modern geometry does is it recognizes it is a group, then it studies this group as a topological group. And because it studies it as a topological group, we are able to do far more in Euclidean geometry that Euclid could never have done. The importance of that is because now all these automorphisms form a topological group. In fact, that group is a Lie group, not just a topical group. We can do calculus on that group. Okay, I must also say that we took a group, abstract group, you could only do group theory. Now you take an abstract group which has a compatible topology, then you can combine algebra with topology. But there are something called Lie groups, in which you can combine algebra with topology with calculus, and so on, so on, so on. And then that becomes more and more realistic structures which are very useful. But these are all different categories. You have to be able to move between these categories. And we have not formalized the name functor because already you are finding this category a bit difficult to digest. I don't know why. But anyway, what can I do? So now let's look at homogeneous topological spaces. So we say that now the definition is obvious. Okay. Let's change the color. A topological space X is called homogeneous if given any 2 points, they could be one and the same, of course, X and Y belong to X, there exists a homeomorphism, which is the isomorphism in this category itself. F from X to X, such that F X equal to Y. So give me some examples of homogeneous topological spaces. Of course, any homogeneous matrix space is a homogeneous topological space. Huh? But let's look at this interval. 0, 1 with usual topology. My question is 0, 1 with the usual metric a homogeneous metric space? Bolo. Is 0, 1 a homogeneous metric space? Tell me. Okay, so is Nilesh Khandekar there? Nilesh, is the open interval 0, 1 a homogeneous metric space?
No.
No. And why not? You're right, it's not. Why not? Try and answer, it's okay. See, the problem is there is a point 1/2, and 1/2 is a point such that on one side of it there is half distance, another side there is half distance available. That midpoint has to go to midpoint if distances are preserved. If you have self-map from 0, 1 to 0, 1, which preserves distances, the midpoint has better go to midpoint, right? Yeah. So you cannot take 1/2 to 1/4, right? Isn't that okay? Under a distance preserving map of the self map of a metric space, an open ball has to map to an open ball, right? And the center to center and so on. Yeah.
So if we take a map to be t to 1 minus t,
E to 1
then
minus t, that has to preserve 1/2, right?
so it
cannot
will
take,
send 1/2 to 1/2.
correct, it cannot send it anywhere else. But if I want a continuous map, you have many other choices, right? Let me draw
Yes,
a
sir.
graph of a continuous map. Here's a continuous map, okay? And I want 1/2, sorry, I want 1/2 to go to 3/4, okay? Now, a very simple map will do it. Define it like this, okay? Define it by this graph, then 1/2 is going to 3/4, right? This map is 1, 1 on 2, and its inverse as this graph, right? Continuous. You don't have to be straight line anymore, right? You
Yes,
can take
sir.
any point to any point. You can make a very funny looking graph as long as it's all the time rising. If it's all the time rising, then it's going to be injective. Yeah?
So 0, 1 should be a homogeneous metric space, right?
No homogeneous topological space. This map does not
Yeah.
preserve distances. समझ गए ना? That's what you explained. This is not a homogeneous metric space, but it's a homogeneous topological space. As a topological space, it is also R. 0, 1 is homeomorphic to R, which is homogeneous. Therefore, this is homogeneous. Right? So do you understand what's a homogeneous topological space? Now give me a non-example, a space which is not homogeneous. Again, this is not homogeneous. Not homogeneous. Even as a topological space. Or how about this? Take the figure of X. This is my topological space. It is exactly the figure that I have drawn. Then you know this point is rather spatial. This point O cannot be taken under homeomorphism to anything else. Any self-homeomorphism, any continuous distortion into itself cannot move O anywhere else. Figure of X. Not homogeneous. Okay. Now, you guys clearly need to think hard about it because each of this statement is like 1 second, 2 second obvious. Should be 1 second, 2 second obvious, but it's clearly taking longer. I don't know why. Now I'm asking you, is any topological group necessarily a homogeneous topological space? So in groups, have you heard of left translation? You have heard of right translation and left translation in groups, right? So given any x, send it to x times g. This is called right translation. By g. Why is this continuous? Continuous as group multiplication is continuous. What is its inverse given by? The inverse map is given by x maps to, follow.
G inverse X.
No. This should go back to x. Therefore, what is the map?
xg inverse.
Xg inverse, correct. Inverse map. That is also continuous. Okay. And therefore, G is a homogeneous space, because if I want to send x to y, choose G to be equal to x inverse y. Then xg equal to y. So every group is necessarily a homogeneous topological space. You can also try left translation. Left translations also work. You can send x to h times x. So I hope it's clear to you that topological groups are homogeneous. As a result, there is no group structure on the closed interval 0, 1, which will make it a topological group. No group structure possible here. If somebody had simply said, oh, take this topological space, now define a multiplication on it, so that multiplication and inverse are continuous and it's a group, ho nahi sakta, because it's not homogeneous. Okay. Now I'm going to talk of separatedness properties. This T1. So I'll have some topological space X, a topological space. Okay. T1 means, what does T1 mean? Each x belonging to X is a closed point, which, if you want to be more formal, it means X is a closed subset X. Then, if my memory serves me right, then such a space is called a T1 space. The separation property T1 says that every point is a closed point. And the separation property T2 says that X is Hausdorff. So you know clearly T2 implies T1, na? Yeah, any Hausdorff space is separated because given any point X and any point Y, X not equal to Y, they are disjoint neighborhoods. Therefore, complement of X is closed because any point in complement of small x. Okay. So the proof of this is because, let me rapidly remind you, proof of the implication is if X belongs to X, then X minus X is closed. Sorry, is open. Is open. Why? Because given any y belonging to X minus X, X belongs to U, Y belongs to V, U intersection V equal to empty, which shows that V is inside X minus X. So Y belongs to V, which is inside X minus X, which means X minus X is open because around any Y there is such an open neighborhood. So Hausdorff always implies T1. In a Hausdorff topological space, every point is closed. Clear? But now I am saying that for a topological group, T1 and T2 are equivalent. And they are equivalent to the identity being a closed point, identity point of the group being a closed point. That is equivalent to any point being a closed point. Why is this and this equivalent? By translation. By right translation, E goes to G. G is a homogeneous topological space. So any point is like any other point. So one point is closed means every point is closed, because given any other point as a self-homeomorphism taking this point to that point. So if this point is closed in the domain, that point is closed in the codomain. Yeah. So any point is closed, E is closed, these are equivalent. But I'm saying Hausdorff if and only if E is closed. So let's give a proof. Proof should be in darker color. Proof. Okay. Let E be closed. Now I'm going to define a map. Consider the map F from G cross G to G, which sends X comma Y to X, Y inverse. Is that okay? This is continuous. This is continuous. How do you prove this is continuous? Because G cross G has one map to G, which is the first projection, another map to G, which is the second projection. From here to here, there is the map inverse. So this map is continuous and this map is continuous, and therefore this has a resulting map into G cross G, which sends X comma Y to X comma Y inverse. And now from here there is a continuous multiplication map going to G, which goes from here to X, Y inverse. So this shows that X comma Y going to X, Y inverse is continuous. So we proved the continuity of this simply using arrows and universal property of product. We didn't say, hey, take some open neighborhood, call it G, call it U. Now let's prove its inverse image is open. For that, once again recall what is the topology on G cross G. And this is the kind of work I have seen you guys do. When I ask such questions, you just go back to your definitions of topology instead of simply building it on universal properties. Yeah. So you have to base your answers on what you have learned. You have to convert it into the next step. Okay. At this point, let me tell you a story which perhaps some of you have heard. There was a psychologist who wanted to understand how a mathematician thinks and how some other random person thinks. So the psychologist called both of them and showed them how to make tea. So for that, he took a kettle, he heated water in it, then he put in the cup a tea bag and poured the boiling water on it. And then he asked them that he gave them a kettle already full of water, and then he said, make tea. So the random person chosen heated the water in the kettle, and then he poured it on a tea bag in a cup, and yeah, he could make tea. The mathematician just threw away the water from the kettle and said, yeah, done. I have reduced it to an earlier problem which you already showed how to solve. So you have to all the time reduce your problems to earlier problems which have already been solved. Well, that's a joke about this, but you see the efficiency of this reducing things to what you already know in arguments like this, where you are not using definition of continuity anymore, you are not using the definition of product topology anymore, you are simply using the universal property of product and the definition of a topological group, that product and inverse are continuous. Okay, so I have this map continuous, and now I ask you, what is the inverse image under F? So what is F inverse of E? What is it equal to? Bolo.
X6, the diagonal.
Diagonal. See, you started saying XX. You are still talking about points. Who is the one who replied? Name?
Sir, no. Later I said that the diagonal.
You don't remember the word diagonal. All these days we have been talking of diagonal, 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 and you are again back to XX. Which X? So you'll have to say the set of all XX, right?
Sorry, sir.
And that is the diagonal. No, no, no. I want you to reflect how you are not learning. You see, you are simply not learning.
No, sir. I just recognize that diagonal is closed.
No, but this is the diagonal. This inverse image is the diagonal. Why do you again want to go to points XX and whatnot? This is diagonal, right? And
Yes.
this is closed. Therefore, diagonal is closed. And this is the meaning of hausdorffness. As we said, the smart meaning of hausdorffness is diagonal is closed. That was the basic property of hausdorffness. Okay, this means is closed in X cross X. So you see, the proof is very easy. If some arbitrary point G was given to you closed, how will you define the map? You will take the map G cross G to G, sending X comma Y to X times Y inverse times G. Now, what is the inverse image of G? Take this map phi. So, then you will have phi inverse G is equal to diagonal. So here I shouldn't have called it X, I should have called it G. The name of our group was G. Therefore, again, diagonal is closed. I combined the translation with the earlier map. Yeah. So is it clear to you that in a topological group, any point being closed is equivalent to topological grouping hausdorff? Clear? Any questions? So let's see how far I have to go. Today, I am in a hurry, which is why I have tried to what is all this happening here? I don't know. Today I have a meeting to attend at the end of the lecture and I don't want to be late for that. Okay, so I am in a hurry to finish. So exercise, every discrete subgroup of R is cyclic. You understand what I am saying? Here is the group R plus. Can you give me a discrete subgroup of this? Yes, 0. H equal to 0. Then H is a discrete subgroup. Any other?
Integers.
Integers.
Z, any other? How about all multiples of pi?
Z root 2.
Z root 2, fine. All multiples of root 2, all multiples of anything. Set of all n times C, where C belongs to R. This is definitely a discrete subgroup, right? And if C is 0, you simply get this. If C is non-zero, you get an infinite cyclic group. It looks like this. Here is R, and this is 0, this is C, this is 2C, this is 3C, minus C, minus 2C, blah, blah. So these are discrete subgroups of R. The claim is every discrete subgroup is like this. It's cyclic. So do you understand the exercise? I am asking you to prove that given any discrete subgroup, it has to be of this form.
May I ask something, sir, about this exercise?
Sure.
Isn't isn't it enough? Is it enough to show? I think it is enough to show that discrete subgroups are countable. Is that
Well, that depends on your proof, you see. You can never just tell me a two statement and say that that implies another two statement unless you tell me how it implies, because logically any two statement implies every other two statement. Okay. Now,
okay?
so unless you tell me how you are going to go from countable to this, I cannot say anything. Okay. Obviously, it is going to be countable if it is cyclic, no? Now, so is it clear as an exercise? You are supposed to solve this exercise. Every discrete subgroup of R is cyclic. You know what is discrete, you know what is subgroup, and you know what is cyclic. So now prove this is so. Yeah. Mathematics. This is mathematics and not definitions. You see, luckily we are coming to the end of that small vocabulary and concepts of category theory that I taught you. It was really tiny. I don't know. Your mind needs to be stretched if you think that that is something big. But now we are done with that, and now you have to start doing mathematics with that and prove interesting results. So you prove this exercise. Okay. Now my next exercise. Give an injective homomorphism from Z cross Z into R. Okay. Obviously, its image will not be discrete because every discrete subgroup of R is cyclic. Is Z cross Z cyclic?
No, sir.
No. What's the proof it's not cyclic?
A cyclic subgroup has only two generators.
Only how many generators?
A infinite cyclic subgroup has only two generators.
That's not what you want to say. A cyclic group can be generated by a single generator. That's probably what you want to say.
Yes.
We are not asking how many generators it has. It's possible to generate it with a single generator. Then it's called cyclic. Yeah?
Yes.
Now, can you show that Z cross Z is not cyclic?
The henceforth, if it has one single generator, then I'll have to show that.
So why
It
doesn't it have a single generator?
You can. The generator would have to be 1 1, but 1 1 is not a generator.
Then why did you say generator has to be 1 1?
No, if it existed, I'm saying if it existed.
Why?
Yeah,
A
because
false statement implies every statement. So again, if then makes no sense unless you tell me how. समझ गया?
yeah,
So bolo. Why, if at all there was a generator, it has to be 1 comma 1 is your claim. Why?
yes, because you take a comma b as the generator, and
Right.
the idea behind a generator is you keep adding it to itself, you will get everything.
Correct.
Okay, and just take
Adding
now look at
and minus of it, not just
yes,
adding.
yes, of
Yeah.
course.
Then
And you look at now look at the first coordinate.
yes.
Okay, by repeatedly adding a or taking
Yes.
the
Yes.
inverse,
Yeah.
you are supposed to get all the integers, which means it has to be 1.
Yeah.
Now do the same thing on the second coordinate. So that also
Yes.
has to be 1. But this
Yeah.
is just going to span the diagonal, 1, 1.
No, it could have been 1 comma minus 1. It could have been minus 1 comma 1. It could have been minus 1 comma minus 1. Where did
Okay,
you
but
jump to?
there,
No.
yes,
Therefore, your argument is not correct. Now, yes, you have some idea, and therefore I'll leave that exercise to you. That's why it's called exercise. Give an injective. Okay. So first of all, this is not cyclic. Now give me an injective homomorphism from Z cross Z into R. Chalo. So you have to tell me where to send m comma n goes to.
Hello, sir.
Yeah, bolo.
Can I tell something? Yeah.
Yes,
About,
yes.
sir, A comma B is a member of Z cross Z. Then
Right.
can we send it to A plus B root 2?
Wonderful. You gave a very good answer. What's your name?
Sir, Anuj, sir.
Anuj.
Yeah.
Anuj, is the blackboard visible to you?
Yes, sir.
So we have already called it m comma n. So I I'm writing your answer with m and n instead of a and b, but this is your answer. Okay. So Anuj has said that take this homomorphism, and indeed it's an injective homomorphism because m plus n root 2 can near be 0. Can this be equal to 0? If this was equal to 0, well, if m equal to 0, n equal to 0, then it is 0. So 0 of course goes to 0, but can it be 0 for something where either m or n or both are non-zero? No, because that will mean that root 2 is a rational number. Okay. Root 2 will be equal to minus m upon n if n is not equal to 0, which is not possible, right? So n has to be 0, but m plus 0 times root 2 is 0, which means m also has to be 0. So 0, 0 is the only thing which goes to 0, which means the kernel is just 0, 0, which means Anuj's map is injective. Obviously, it's a homomorphism. Okay. So Anuj has already solved it. Now, how does the image of this look? You know, its image is dense.
So it is dense.
The image will be dense. Suppose image was not dense, okay, then you can say around 0 there will be a neighborhood with nothing except 0 in it by translation. I am now talking very fast, but you can make it precise. Okay, if image is not dense, it will be forced to be discrete, is what I am arguing, and therefore cyclic. Okay. Now, let's talk of subgroups of a topological group. Here, this is a subgroup of this topological group, right? And this subgroup, its induced topology is not the discrete topology. This is dense. So the induced topology on it is not discrete. In the neighborhood of any point, there are lots of other points. Okay. Now, suppose G is a topological group, H is an abstract subgroup. Then let us give H the subspace topology, the induced topology. Then H is again a topological group, and the inclusion is a continuous group homomorphism. This should be pretty obvious to you, so I am going to call it easy exercise. Okay. This is the kind of thing perhaps you are used to being asked in your exams. I don't know what they ask you in your exam. Perhaps they ask pre-prepared, pre-taught theorems and their proofs which you can read and memorize, or they ask you very easy exercises, one or the other. Okay. All right. So this is an easy exercise. Show it. Writing G is a topological group, H is an abstract group, give H the induced topology. And this is a topological group, and the inclusion is a continuous group homomorphism. So it looks like I have now come to the last statement I have planned for today because I want to go early. So I am making the following claim. Let G be a topological group such that G is Hausdorff. Okay. And let H be any subgroup such that H is discrete in the induced topology. Then I am claiming H is closed. Okay. So here is an example. Suppose X equal to R, usual topology. I am going to give a subspace Y, topological subspace. Now, give an example. Where Y is closed in R, but, sorry, I want it the other way around. Y is discrete Y is discrete in the induced topology but not closed in R. Give me a discrete subset which is not closed. I want a discrete subset of R which is not closed. समझ गया? Somebody willing to give me an example? बोलो.
The set 1 by n where n belongs
Wonderful.
to n.
Who was answering? This is the right
Yes,
answer. Yeah. So what's your name?
Roshni.
Sorry, can't. Roshni. Roshni, you have given a wonderful answer. So take the set 1, 1/2, 1/3, blah, 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 blah. This set. Okay. Take this as a subset of R. This is discrete, but not closed. So Roshni has given us an example of the kind of phenomenon I'm talking about. But now you see the importance of this hypothesis. G is a topological group, which is Hausdorff, and H is a subgroup, not an arbitrary subspace, but a subgroup such that it is discrete in the induced topology. Then H is closed. You see, this is not a subgroup. So let us give a proof of this. Proof. So I will draw my G like this. This is G. And I'm going to draw H like this. This is H. And now I know that G is Hausdorff, right? Okay. So using G is Hausdorff, I am going to do something nice. Therefore, I know, and I know H is discrete. So using this, I am going to produce something like this. So because H is discrete, there exists an open neighborhood E belongs to U is contained in G such that U intersection with H is just this single point E. Why is there such a neighborhood? Because H is discrete. Because H is discrete, the identity point is open in H. Therefore, it has a neighborhood which has only that point in it. And what are neighborhoods in H? They are intersections with H of neighborhoods in G. So there is a neighborhood U of E whose intersection with H is this. And now by continuity, there exists an open neighborhood E belongs to V is contained in U such that V times V inverse is contained in U. So what is V times V inverse? V times V inverse is the set of all x comma y inverse such that x belongs to V. Why? Because the map from G cross G to G, which sends x comma y to xy inverse, is continuous. So if I take the neighborhood U, its inverse image is continuous, and the inverse image contains the point E comma E. E comma E goes there, right? So there is some open neighborhood V and some open neighborhood W, so that V times W inverse goes into U. But now you replace V by V intersection W, and so that times its own inverse goes in U. So this is what happens. So now I want to claim that given any G belonging to G, okay, take the neighborhood Okay, I might make a left-right mistake, then I'll correct it. Take the neighborhood G times V. This left translation of V by G. Now suppose I need 2 points. Suppose I have 2 points H1 and H2, which are in H. Suppose they belong to the neighborhood GV. Okay, then H1 is going to be G times V1, H2 is going to be G times V2, and therefore H1 inverse H2. Now I see that I should have done it the other way around. Okay, H1 inverse H2 is V1 inverse V2. Okay, so having come to grief by putting this on the right hand side, I am going to put it on the left hand side. Okay, so take the neighborhood V times G, and suppose there are 2 points in V times G. Then H1 is equal to V1 times G, H2 is equal to V2 times G. Therefore, H1 times H2 inverse will be equal to V1 times V2 inverse. Agreed? And now this belongs to H. On the other hand, this belongs to V times V inverse, which is contained in U. And you know that H intersection U is equal to identity. Therefore, H1, H2 inverse is equal to identity. So H1 equal to H2. So the moral of the story is each G belonging to G has an open neighborhood, namely V times G, such that there is at most one point of H in VG. Therefore, H is closed. Okay. How do I know this? Because I'll take a smaller neighborhood and smaller neighborhood. It's Hausdorff. I can always leave out some points. And so I'm using the general fact. Let me call it exercise. Exercise. Let X be a topical space Y a subset. Suppose that there's some point X which belongs to Y closure minus Y, a limit point of Y that is outside Y. Then you know that if I take this point X and take any neighborhood of it, because it's a limit point, there will be some point Y here. Okay. Sorry, there will be some point Y here. Now suppose that if X is Hausdorff, then any neighborhood of X contains infinitely many points of Y. Because now I have got one point. Now because it is Hausdorff, I can choose a smaller neighborhood which leaves it out. But then there's a point inside there. So you may call this point Y0, this point Y1, next Y2, and so on, So you end up having infinitely many points in that neighborhood. See this think in metric space terms. If you are more, see, when you are thinking of Hausdorff spaces, intuitively you can think of metric spaces to help your argument. So if I have got a metric space and I have got a set and I have got a limit point which is outside that set, then there's a sequence converging to that limit point. And then in a small ball around that limit point, there are infinitely many points because they go closer and closer and closer. On the other hand, here we proved that there is at most one point in that neighborhood. If there are 2 points, they are equal to each other. And hence, that cannot be. And therefore, there are no such limit points which are outside H, which means H is closed in G, which means I have proved this. Okay. So this is the QED for the statement. So this is it, guys, and I won't say any questions out here because today I want to go early. And anyway, you guys seem rather, well, towards the end you started answering, but some energy level is low. Perhaps is this course getting too heavy? You have to give appropriate feedback to the organizers on this. Anyway, all right. So this is it, and remember next week, and I'm going to write it here. I'm actually going to write it here in red. See you on Monday, 20 December, I believe, at 3:30. Am I right? So my next lecture is on Monday instead of being Wednesday. Next week's timetable is slightly different, and so my lecture is Monday. So see you guys on Monday. I won't ask any questions. I'll simply say bye-bye. So that's it.